By now you've watched the proof. If you haven't watched the proof, go back and watch it now. But here is the outcome. A pendulum is simple harmonic motion in the special case that we don't pull it back to a really large angle, or we keep the angle small. Realistically, 15 degrees or less. And realistically, I'm not going to try and trick you. If I give you a pendulum question, assume that the pendulum works with the equations we've got. We could show that the force is equal to K times S, with the K equal to this mg over L term. There's some examples there for you to try, but I'm going to scroll back up. I'll just, before you set loose on those examples, I'm going to show you how this works. Basically, the coolness is all of our simple harmonic motion equations will work for a pendulum. Just wherever we see the letter K, we need to sub in mg over L. So if we go back up here, scroll, here we go. I'm not going to go through all of them, but let's pick on, this is kind of a common one. The time period of something going through simple harmonic motion is 2 pi root m over k. For a pendulum, we know that k, we just figured out, is mg over L. So our time period equation turns into t equals 2 pi m over mg over L. Okay, way back you did some rational expressions because nobody likes fractions underneath fractions. I'll talk you through it. You'll get the hang of it because we'll be doing it a few times. But this m on the numerator cancels out with this m because it's on the denominator. So now if we want to rewrite it, we've got 2 pi root 1 over g over L. 1 over g over L, you could invert and multiply, or you can think about inverses. 1 over anything means you flip it over, but the L on the denominator of the denominator is going to flip all the way to the numerator, and we're going to get a new equation for the pendulum that t equals 2 pi root L over g. If I were you, I wouldn't memorize a whole bunch of new equations. You don't have to memorize equations, period. But if you keep these equations handy, or document where these are, this group of 5 of them, just have those available and know that for a pendulum, if it's a pendulum question, you have to sub in k equals mg over L. And then just create your new equation and crunch it out and figure out whatever the question's asking. I'm going to scroll back down again. Oh, before I scroll, way back when we did that pendulum lab near the start of the quadmester, this is the answer you Googled when you were doing your graph work. The equation you Googled for that graph work, for the theoretical side. Okay, scrolling back down, you can try these examples now or work through these examples now. You've already got the equation for time period. There's an equation up there for maximum speed, just sub in mg over L. There's an equation for x at a specific time. It's that a cos omega t thing. Omega's got a k in it, so just sub in mg over L into your omega. That's kind of how simple harmonic motion works. Before I wrap up the video, take some time, go over pendulums. Before I wrap up the video, this whole simple harmonic motion topic is weird. And we don't go too far in high school. We just talk about springs and pendulums. Where you'll see it next, depending what you take in university. But if you take some physics courses or some chemistry courses where you get deeper into quantum, when people study quantum physics, quantum chemistry, and they talk about vibration of subatomic particles and weird things like that, simple harmonic motion actually shows up when they model the atom at that sort of complex level. And then a silly one, you can watch the video here. If we assume that the Earth was completely uniform in density, it's not. But if we assume that the Earth is completely uniform in density, if you could drill a hole all the way through Earth, the way gravity works, if you jumped into that hole or dropped something into that hole, it's going to wobble up and down through the Earth, kind of like a pendulum swinging back and forth or a cart on a spring swinging back and forth. It's going to exactly follow simple harmonic motion as long as we assume this uniform density thing, which is just kind of a cool, not realistic, but a cool way to apply equations. So I'm going to pause this video here. We're officially done our simple harmonic motion note. Work through those two examples and try the worksheet and the check-in, and Then you're moving on to the unit wrap-up. Email if anything's bugging you.